In the last video, we had posed a problem. The link is in the description box below. Here is a quick recap. If a tilted pencil is immersed partially in water, it looks bent. Why? The common answer is to consider a ray diagram like this. But if this were really the correct explanation, then a vertical pencil should also appear extremely bent like this. Experiment shows that a vertical pencil appears vertical, irrespective of the angle of viewing, though it appears shorter. We shall solve this vertical case first. The solution that I am going to discuss is not entirely my own. One key idea was suggested to me by Professor Mrinal Nandi of West Bengal State University. We shall start with a careful rethinking of what is meant by virtual image of an object. Our first brush with virtual images occur when we learn about flat mirrors. Light rays emanating from a point after reflection appear to emanate from another point. So, this point is called the virtual image of this point. Somehow from this, many of us end up believing that the definition of virtual image for any general optical system is like this. The system is like a machine into which are fed rays emanating from some point. The rays come out of the system after some distortion. If they appear to emanate from a different point, then our eye thinks that this point is the virtual image of that point. While this is correct, this is not the most general situation where the eye sees a virtual image. All the outgoing rays need not be concurrent like this. It is just one case, the simplest case. It is quite possible that the rays emanating from a point do not appear to come from a common point after passing through the optical system. Even then, in certain situations, our eye may see a virtual image. These, for example, do not pass through any common point. Notice they are intersection points. These points we shall call the candidates. Each candidate has at least two rays passing through it. We shall say that those rays are voting for that candidate. For example, this candidate has 2 votes, while this candidate has got 3 votes. Notice that the same ray may vote for multiple candidates, like this ray is voting for this as well as this candidate. The crux of the solution is that if there is one candidate with overwhelming number of rays voting for it, then the brain will pick that as the position of the virtual image, ignoring the other minor candidates like this. This is the second possibility. But what happens if there are multiple strong candidates like this? Here, the virtual image will appear to change position as we move our eye. When the eye is here, then our brain interprets this as the most popular candidate. So we see the virtual image here. But when the eye moves here, now the virtual image appears to change position from here to here. This is the third case. The situation could be even more general, but this is all that we shall need to solve our problem. Consider this single ray. We are showing it in 2D, but the true setup is in 3D. In particular, if we rotate this ray like this, we get lots of other rays all making the same angles with the water surface. If we extend all the green virtual rays backwards, then by symmetry, they intersect at a point vertically above the true point. Notice how these virtual rays form an inverted cone with the intersection point at the apex. Thus, the apex is a candidate with an infinite number of rays voting for it. Of course, not all of these enter our eye because they are coming out in different directions. However, since our eye, the iris of our eye, has some positive diameter, a narrow pencil of these rays gets in. And since there is a continuum of such rays, even that narrow pencil has infinitely many such rays in it. Now let's get back to the diagram that is typically provided in textbooks, like the one in Jenkins and White. This is our familiar 2D diagram, though we have shown it in 3D. It is true that this point is also a candidate, but it is voted by just 2 rays. Here also you may rotate the 2 rays in 3D to get a fan of rays, but since the candidate is not on the axis of rotation, the candidate also got rotated to a different position. So each of these pairs of rays will actually vote for a different candidate. Thus, the earlier candidate was the only one with infinitely many voters, while all these infinitely many candidates have just 2 voters each. Little wonder that the weaker candidates will be ignored by our brain in favor of the popular central candidate. Textbooks generally confine their explanations to 2D diagrams. But unfortunately, the infinitely many voters of the winning candidate are not all on the same plane as they form this conical structure. This blue rectangle here is the water surface. A moment's thought will convince you that no 3 of these green virtual rays are in the same plane. That is why all textbooks using only 2D diagrams get it wrong. You have to think in 3D to get the correct answer. So far, we are talking about only the vertical pencil case. What if it were tilted? We hardly need to do any extra work. Using the same notion of conical fan-out of rays, we know that any point has a virtual image vertically above itself. The image of the red point is at the green point. We are going to apply this to every point of the tilted pencil. Now, as the entire fan-out is hard to draw at every point, it will give rise to an awful clutter. We shall devise a quick way to find the image point. Suppose that we want to locate the virtual image of this point underwater when we are looking from this position. We shall first draw a ray from the point to the eye following the laws of refraction and also the vertical. Then we extend the diffracted ray backwards to intersect the vertical. Then this point where the 2 things intersect will be the virtual image of the red point. We shall now carry this out for every point of the pencil underwater. That is, we shall move this point all along the pencil. This red curve that you see is the locus or the set of all the image points. Thus, this is how the pencil would appear to the eye. Notice that this is not entirely a straight line, though very nearly so. Well, That's basically the solution that I wanted to present in this video. I shall finish with a couple of minor points. We have done all our discussion assuming that we are looking with a single eye. Actually, that is not essential. If you look with both eyes open and your head vertical, not like this or this, then both the eyes will be on the same horizontal level. So the rays picked up by the two eyes will come from the same cone. As all these rays will still vote for the same apex, the image will actually be reinforced. That was the first point. The second point is that we often think of science, at least basic science, as a completely settled subject, where all the decisions have already been made by the famous scientists to everybody's utter satisfaction. Thus, we approach learning basic science with a passive mind. Even when we carry out the experiments given in textbooks, we do so with our thinking switched off. The conclusions are already given in the books, and the experiments appear to be more of a ritual than something calling for active exploration. Well, this little puzzle shows that even internationally acclaimed textbooks sometimes get the basic things wrong. In spite of all the great scientists ever born, our own little brains are still not as useless as it might seem.